Hello, this is Dr. Joe Trout from the physics program at the Richard Stockton College of New Jersey. In this lecture we'll discuss Chapter 3, and the topics will be solar and terrestrial radiation. We know that heat can be transferred in three ways, by three processes. The first is conduction. This is when we have two bodies in contact, and heat will flow from the hotter body to the colder body. So conduction involves things that are two things to be in contact with one another. There's also convection. Convection is where we heat a fluid, and then the fluid moves, bringing the heat with it. So for instance, if you've ever seen a radiator heating a room, they're always on one side of the room. And the reason is that we heat the air above the radiator, it expands, it becomes buoyant and moves up, and then the cold air comes in, fills in. So this is convection, where we heat a fluid and the fluid moves. And by fluid we mean either a liquid or a gas. If we think of the energy we're getting from the sun, it definitely is in conduction because we're not touching the sun. And it is in convection because there's no fluid moving between the sun and us. So that brings around the third type of energy transfer or heat transfer, and this is known as radiation. Radiation is heat transfer by electromagnetic waves. So in this chapter we'll talk about energy, and when a physicist talks about energy, they're talking about the ability to do work. There's multiple forms of energy. For instance, there's kinetic energy. This is energy due to motion. So we have, say, kinetic energy is equal to 1/2 the mass of the object times its velocity squared. We also have potential energy. So if I lift something from the surface of the earth and I let it go, the potential energy that it had can become kinetic energy. And this has the ability to do work. So for instance, if I'm trying to drive a fence post into the ground, I can lift a heavy object like a hammer and then let that hammer fall and drive that fence post into the ground. So the hammer had a potential energy due to its distance from the earth, and that potential energy gave it the ability to do some work, which was to drive the fence post into the ground. There's also heat energy, chemical energy, electrical energy. There's many forms of energy. We'll also talk about the first law of thermodynamics, which is a restatement of a really important law in physics known as conservation of energy. And the first law of thermodynamics says that energy cannot be created or destroyed. It can only be converted from one form to another. So for example, if I pick up a baseball and I raise it 2 meters above the earth, it has potential energy. If I let it go, it'll lose that potential energy and gain kinetic energy. Another example is that we have heat coming in from the sun, and that heat energy can become kinetic energy of the winds. In this chapter we will also talk about electromagnetic radiations and the laws that govern it. We'll talk about how this reacts with the Earth atmosphere system, the conversion of solar radiation to heat, and the emission of infrared radiation. And when we think of infrared, normally think of heat. And finally, we'll talk about the greenhouse effect. So first we need to make some definitions. The first one is electromagnetic radiation. That's energy transmitted through space or materials as waves. And it has both electrical and magnetic properties. So if we see light, that's an electromagnetic wave. We'll also talk about the electromagnetic spectrum. So light is one form of electromagnetic wave. There's many other forms, such as radio and TV waves, microwaves, infrared radiation, visible light, ultraviolet radiation, and X-rays and gamma rays. These are all electromagnetic waves, and they're part of the electromagnetic spectrum. They differ in their wavelength. So the wavelength is a distance between successive waves, crests or troughs. Another way we could define these waves is by their frequency. All of these waves move at the speed of light in a vacuum. The frequency is the number of wave crests that pass any given point per second, and they're measured in hertz, and the abbreviation for hertz is capital HZ. This is in honor of the scientist who worked a lot with waves and came up with this unit. We find that the frequency is actually inversely proportional to the wavelength. So if you have a long wavelength, you have a short frequency or a low frequency, a few waves per second. If you have a short wavelength, you have a high frequency, many waves per second. The speed of the electromagnetic radiation in a vacuum is the speed of light, and it's 3 times 10 to the 8th meters per second, or 300,000 kilometers per second, or 186,000 miles per second. When we talked about light, we're usually familiar with the visible spectrum, so the colors red and blue and purple and green. We also have ultraviolet, that's shortwave radiation, and it means beyond violet. And infrared means below red. This is long wave radiation. What we're going to find is that a lot of the energy that comes from the sun, the atmosphere is transparent to, so it passes right through the atmosphere. What happens is it strikes the Earth's surface. The Earth's surface warms up, and then it re-radiates energy back out at a longer wavelength, and this heats the atmosphere. So once again, most of the energy makes it through the atmosphere, strikes the Earth warms up, the Earth warms the atmosphere. So here's a picture of the electromagnetic spectrum. What you see is that the visible light is a very small part of this spectrum. The visible spectrum, the longest wavelength is red, and it's about 700 nanometers, or 0.7 micrometers. And the shortest wavelength is purple. That's about 400 nanometers, or 0.4 micrometers. See that radio waves are very long. They can go 10,000 kilometers to about a meter. Then comes microwaves, then infrared radiation, then the visible spectrum, then ultraviolet, X-ray, and gamma ray. Gamma rays are very short wavelength. They're about 0.0001 micrometers. We find that the shorter the wavelength, the more energy the wave has. So for instance, we have all these radio stations around sending out radio waves, and they don't do us much harm. They're very long wavelengths. Gamma rays are rays off of nuclear decay, and these can cause us actually damage to our body. The wavelengths are very short. Radio waves are made by producing electromagnetic waves using things called inductors and capacitors. Microwaves, we use it for cooking, of course, but we also use it for communication. Infrared radiation is pretty much heat. So when you think infrared, think of heat. Ultraviolet radiation, a good source is the sun. And we'll see we have the ozone layer that protects us from really strong ultraviolet radiation. This is also what causes sunburn. Everybody knows that too many X-rays could be bad for you. Right, and how X-rays are made is we take an electron, get it moving really fast, and smack it into a piece of a tough piece of metal. And X-rays are given off. Finally, gamma rays are the shortest wavelength, and they come from nuclear decay, and these can definitely make us sick. So here shows our picture of a wave. We usually think of a crest, so it's going above. If you think of this as an ocean wave, for instance, this is the point that it makes above the equilibrium position, and a trough, this is the point it makes below an equilibrium position. We see that the long waves have a few wavelengths per second, so they have a low frequency. Short waves have many wavelengths per second, they have a high frequency. So the wavelength is inversely proportional to the wave frequency. If the wavelength is long, the frequency is low. If the wavelength is short, the frequency is high. As we said, we have visible radiation. That's the portion of the radiation of the spectrum that we can see with the human eye. And its short end is violet. That's about 0.4 micrometers. And the long waves are red. They're about 0.7 micrometers. A micrometer is 10 to the minus 6 meters, or 1/1,000,000th of a meter. As we said, microwave radiation is used in microwave ovens to heat food. It's also used in radio communications. And radio waves have wavelengths which range from a fraction of a centimeter to hundreds of kilometers. So we need a few more definitions. One is a black body. A black body at a constant temperature absorbs all the radiation it receives and emits the energy it absorbs. So when we have a black body, it can accept all forms of energy. We call it a perfect absorber and a perfect emitter. So think of it this way. If the sun comes in and it heats a body, that body gets hot and then it re-radiates out energy. The surfaces of real objects may approximate black body for certain wavelengths of radiation. So to make all of this mathematical law simple, the wavelength of most intense radiation emitted by a black body is inversely proportional to its absolute temperature. So both the Sun and the Earth are nearly black bodies. The Sun is much hotter than the Earth, therefore its most intense radiation comes at a shorter wavelength. So don't forget, we said short wavelength, high energy, long wavelength, low energy. So here we see the amplitude, so how much of each wavelength is coming from different stars. And there's a star that is 4,000 Kelvin, another star that's 5,000 Kelvin, and a third one that's 6,000 Kelvin. If we see the one with the lowest temperature, the 4,000 Kelvin, it peaks around the red edge of the spectrum. Okay, so it has all these wavelengths, and this is how much of the wavelengths it has, but it peaks at about 400. And that wavelength is about 0.7 micrometers. If we look at the hottest star, it peaks somewhere around blue, and this is about 0.4 micrometers. So once again, the shorter the wavelength, the more energy, or the hotter the star is. Right, so if we look at the total energy flux, that's the energy per area per time, emitted by a black body across all its wavelengths, it's proportional to T to the fourth. This first diagram shows the flux of the radiation at the top of the atmosphere. It's the red line here. And an ideal radiator is this black line here. If we look at the Earth, it radiates out energy at about 10 micrometers, and the temperature is about 288 Kelvin. So this is about 17 degrees C. I'm sorry, about 12 degrees C. No, I'm sorry, it is 17 degrees C. It's that's about the temperature of the Earth. We also see that the intensity drops as 1 over r squared. So if we double the distance to this from the Sun, it reduces the radiation by a quarter. The Sun's composed of hydrogen and helium, and the energy we get from the Sun comes as a byproduct from a nuclear fusion reaction. Nuclear fission is where we break an atom apart. Nuclear fusion is where we push them together. So what we see is that 4 hydrogen protons fuse together to form one helium nucleus. The excess mass in this fusion reaction is converted to energy, where the energy is equal to mc squared, where m is the mass that was lost, and c is the speed of light. And this equation came from Einstein, so E equals mc squared. Some of the energy is used to bind the helium nucleus. The rest is radiated off by the Sun's surface into space. The visible surface of the Sun, we call the photosphere, is cooler than the interior, and it is convective. So in the center of the Sun we have very hot fluid. It moves out towards the outside edges of the Sun, and the cool outside edges come into the center again, and we have this convection going on. These convection cells are called granulars. We also have sunspots. These are cool areas of the sun. What happens is they have a very intense magnetic field, and we end up with these cool spots in the sun called sunspots. If there's a few of them, then the sun's pretty hot. If there's more of them, the sun cools off a little bit, or at least the amount of energy we see is a little less. So the change in the number of sunspots can affect the Earth's climate. Off of the top of the visible surface of the sun, there's the chromosphere. This is the sun's atmosphere, and it's made up of superheated gases, mostly hydrogen and helium. And the corona is the outermost portion of the sun's atmosphere. So we have the surface, just like the surface of the Earth, only this is called the photosphere. Then the Earth's atmosphere, which is called the chromosphere, and then the very top of the sun's atmosphere is called the corona. Most of the Earth's weather is due to differential heating from the sun. So think of it this way. If you've ever been on a stage and seen a spotlight, if the spotlight shines straight down, like flashlight A in our picture here, what you get is a very tight, bright white circle. So you get a lot of energy over a very small circle, or a very small area. If you tilt that flashlight or spotlight to be in position B, what you see is that same amount of energy gets spread over a larger area. This concentrated energy provides for more heat per unit surface area, which would equal a hotter ground temperature. So you know when the sun's directly overhead, it gets very hot where you are. And when the sun starts to go down and starts to set, that same amount of energy is spread over a larger area, and it cools off a little bit. We also see this happening as the sun hits directly at the equator, and the equator is pretty warm, and it hits less directly at the poles, and they're pretty cold. So what happens is we have the noon solar altitude always varies with the latitude because of the Earth, presents a curved surface to this incoming solar radiation. So as the energy comes in from the sun, it strikes the equator head on, just like that flashlight we'd shown with the previous slide. That's in position A. If we look further north, what happens is it's spread over a larger area because it provides a curved surface to the sun. So the equator is very hot, and the poles are relatively cool. We also see that the sun's energy that hits the equator runs through just a little bit of the atmosphere, right? It shows distance x here. But if we move up towards the pole, that same amount of energy has traveled further through the atmosphere. And what we'll see is that some of this energy is absorbed and reflected by things in the atmosphere, such as clouds. So if we look at the average solar radiation by month, if we look at Singapore, that's just above the equator. And we end up with a daily solar radiation of about 400 calories per centimeter squared per day. And it's pretty constant. It doesn't change as the seasons change very much. If we look at New York, this is about mid-latitude, right halfway roughly between the equator and the pole. And what we see is that in the winter, we only get about 100 calories per centimeter squared per day. In the summer, we go up to about 500 calorie per centimeter squared per day. And then we're back down to 100 when it becomes winter again. In Antarctica, what happens is in December, we have about 450 calories per centimeter squared per day. And then it goes down to 0 somewhere around March. And it stays at 0 till about September when it starts rising again. So the intensity of solar radiation striking the local Earth surface varies over the year. And the inclination of the Earth's axis causes the northern hemisphere to be tilted towards the sun for part of the year and away from the sun for part of the year. When the North Pole is tilted towards the sun, the northern hemisphere receives more solar radiation, and it's spring or summer in the northern hemisphere. When the North Pole is tilted away, the northern hemisphere receives less solar radiation, and this is fall or winter in the northern hemisphere. At June 21st, we have the solstice of the sun is directly overhead at the Tropic of Cancer, about 23.5 north latitude. This is the beginning of the northern hemisphere's summer. At the September 23rd equinox, the sun is directly overhead, 90 degrees at the equator. So this is 0 degrees latitude. And this is the beginning of the northern hemisphere's fall season. December 21st is the solstice of the sun is directly overhead the Tropic of Cancer. This is 23.5 degrees south latitude, and it's the beginning of the northern hemisphere's winter. And at March 21st equinox, the sun is directly overhead the equator again, and it's the beginning of the northern hemisphere's spring. So this diagram is a little bit misleading because it shows this oval that has a very large extent, right? A very large eccentricity. Really, the two foci are most closer together. The sun lies at one of the foci, so it isn't as dramatic as this looks. But here shows the position of the sun at the winter solstice, December 21st. The two equinox at the 23rd of September and the 21st of March, and the summer solstice at June 21st. So we see is that during our winter, the northern hemisphere's winter, we're actually closer to the sun than during the summer. However, during the winter, the north pole of the Earth is tilted away from the sun, so we're getting less direct sunlight, and the southern hemisphere is getting more direct sunlight. During our summer, we're tilted towards the sun, so the northern hemisphere is tilted towards the sun. We're getting more direct sunlight, and the southern hemisphere is tilted away from the sun. It's getting less direct sunlight. So we see the summer solstice, we're tilted towards the sun. The winter solstice, we're tilted away from the sun. And during the equinox, the sun is hitting directly at the equator, and we're both getting equal. The northern hemisphere and the southern hemisphere is getting equal amounts of sunlight, or equal intensity. Here shows the path of the sun. So at the equator, the sun is always pretty much directly overhead. It just might shift north or south a little bit. In the northern hemisphere, what we see is that in June, the sun is at its largest angle, right? So almost perpendicular to the Earth, and we're getting a lot of direct sunlight. In the winter, that angle increases, and we're getting less sunlight. In the North Pole, part of the year we get no sunlight at all. Here shows the variation in length of daylight, and it increases with increasing latitude. So for example, if we look at Caracas, which is about 11 degrees north of the equator, there's a slight change from summer to winter, but it's pretty much 12 hours a day. As we move up to Edmonton, which is at about 54 degrees north, in the winter we get about 7 hours of daylight, and in the summer we get about 17 hours of daylight. So the change in daylight hours between winter and summer becomes more extreme as we move away from the equator. We also have something called the solar constant, and this is the rate at which solar radiation falls on the surface that would be located at the outer edge of the atmosphere. So for instance, it's the energy that would strike this circle here if the Earth was flat. It averages about 1.97 calories per square centimeter per meter, or about 1369 watts per square meter. So now we have sunlight coming in from the sun and hitting the Earth, and first it goes through the atmosphere. Some of the solar radiation passing through the Earth's atmosphere interacts with gases and aerosols via scattering and reflection and absorption. So some of it is just scattered. That explains why the sky is blue. Some of it is reflected straight back out into space, and some of it is absorbed, causing whatever that absorbs it to warm up. Don't forget, we said energy must be conserved. So if we look in the Earth's atmosphere, if we look at the percent of radiation that's absorbed, called the absorptivity, plus the percent that's scattered or reflected, we call the albedo, plus the percent that's transmitted to the Earth's surface, we call that transmissivity, has to equal 100% of the energy coming in from the sun. First we have scattering taking place, so the particles can disperse solar radiation. And the scattering is wavelength dependent. There's more scattering of blue light by oxygen and nitrogen molecules, which is what our atmosphere is made of. That's why we have a blue sky. Whenever we have an interface between two medium, so for instance air and a cloud, we'll get some reflection. The amount of reflected light divided by the amount of incident light equals the albedo. We also have absorption. So the atmosphere is actually pretty transparent to most of what the sun delivers to the earth, so it doesn't get absorbed by the atmosphere. Absorption will convert radiation to heat energy. So for instance, ultraviolet absorbed in the stratosphere, there's chemical reactions involved in the formation and dissociation of ozone. This significantly reduces the intensity of UV that reaches the Earth's surface. It also is why the stratosphere warms a little bit. So for ozone production, what happens is we have two oxygen molecules, and we said they're diatomic molecules. Ozone comes in and strikes this oxygen molecule. It splits the two oxygen atoms apart. Now we have two free oxygen molecules that are moving pretty fast. They smack into two free oxygen to another oxygen molecule, and we're left with three oxygen atoms that have formed a molecule. Also, what can happen is we have ozone, that's three oxygen atoms that form a molecule. The ultraviolet radiation comes in, it splits off one of the oxygen molecules. This oxygen molecule is now moving very fast. It smacks into another ozone molecule, and we're left with two oxygen molecules of two oxygen atoms each. The question is, why is the southern hemisphere spraying ozone hole over Antarctica? So what happens is a circumpolar vortex cuts off the Antarctic atmosphere, and it loses ozone through the absorption of UV light or UV radiation. The circumpolar vortex weakens in spring, so we have warmer ozone-rich air invades, and it replenishes the ozone. In the cold Arctic stratosphere, with stratospheric ice, accelerates the reaction with CFCs as a catalyst. So there's no comparable ozone hole in the Arctic due to the warmer temperatures and the weaker circumpolar vortex. The Montreal Protocol was an international agreement to limit CFC production, and violators receive economic sanctions from the other countries. Here shows the ozone hole in millions of square kilometers. If we look at 2007, we see that the ozone hole started in late August and peaked about mid-September at about 26 millions of square kilometers. In 2008, shows the blue line, and the purple line shows the mean from 1998 to 2007. The dotted line shows the minimum, and the solid line shows the maximum. So we see that chemicals that threaten the ozone have both natural and industrial sources. So what can happen is if we get a really strong convective thunderstorm, we can break through the top of the tropopause and give in gases into the stratosphere. Volcanic eruptions can do the same thing. They can send CO2 into the atmosphere. And CFCs that are produced by, that are man-made source, can also get driven up into the atmosphere. Solar radiation hits the Earth's surface, and some of it is absorbed and some of it's reflected. The lighter the surface, the higher the surface albedo. So don't forget, the albedo is the amount of light reflected divided by the amount of light that comes in. So the albedo can vary with solar altitude. So for an example, if you've ever been on a lake when the sun was going down, you'll see that there you get really sharp and high reflection off of the water surface, which is not there at noontime. So as we near sunrise and sunset, we almost get 100% reflection. So our albedo would be 1. This decreases rapidly as the solar altitude increases. So when you think about it, when we have the most trouble with reflections off of buildings or other cars are during sunrise and sunset. This is when the angle of the sun is at its lowest. The global average for the oceanic albedo is about 8%. So that means only 8% is reflected. 92% of it is absorbed. Here shows a table of some of the different albedos. Right? We see that in cirrus clouds we're reflecting 40 to 50% of the energy that's coming in. If we look at soil, we're reflecting about 5 to 30%. Snow reflects about 75 to 95%. And water, it varies, but what we see is that if we have a high solar altitude, for instance at noontime, we don't have very much reflected, about 3 to 10%. As the angle of the sun goes down, we end up with 10 to 100%. Notice that the forests are between 7 and 18%, and that's how much energy is reflected off of these surfaces. Water tends to absorb red light more efficiently than green or blue. More green and blue light is scattered to our eyes. This explains why the ocean has a bluish color. Any of you who are divers know that as you go down deeper, right, you start to lose the red and yellows and things become very gray and bluish looking. So energy comes in from the sun. Some of it's reflected by the Earth's atmosphere system. That's about 31%. About 20% is directly absorbed by the atmosphere. So about half of the energy, about 49%, hits the Earth's surface. So some of the energy is reflected right away. A small portion is absorbed by the atmosphere. Most of it hits the Earth's surface, the Earth warms, and re-radiates out energy. We could talk about the global radiative equilibrium. This says that the solar radiation heating of the Earth atmosphere system is balanced by the emission of the heat to space in the form of infrared radiation. So we assume that there's kind of an equilibrium. The sun supplies energy to the Earth re-radiates out the energy at a different wavelength. This was the subject of an experiment using a satellite called the ERBI, the Earth Radiation Budget. And what it did was measure the amount of energy coming in from the sun and remeasured the amount of energy going out from the Earth. If there is more coming in from the sun than going out by the Earth, then we'd assume that the Earth was warming. And if there is more going out from the Earth than coming in from the sun, we'd assume the Earth is cooling. If they were both equal, we'd assume that the Earth's temperature wasn't changing much at all. Now we want to talk about the greenhouse effect. So this is the heating of the Earth's surface in the lower atmosphere by strong absorption and emission of infrared radiation caused by certain atmospheric gases. So some gases absorb energy more efficiently than other gases, and these gases are called greenhouse gases. So the sunlight comes in. It's at a wavelength that the atmosphere doesn't pick up very well, so it doesn't absorb that energy very well. It hits the Earth's surface. The Earth's surface warms and radiates out energy at a longer wavelength, which can be absorbed by the atmosphere, and especially these greenhouse gases. Greenhouse gases are transparent to the shortwave radiation coming in, but they absorb the long wave radiation being emitted by the Earth. So the Earth is kept warm by these greenhouse gases. If we had no greenhouse gases, then the Earth would become very cold and life would not exist. Here shows some of the greenhouse gases and where they absorb in the spectrum. So, there's a theory that the global climate change can be brought about by the enhancements of the Earth's natural greenhouse effect by increasing the levels of the atmospheric CO2 from man-made sources. Systematic monitoring began back in 1957. Here shows the results of that study, and we see that it oscillates as the year oscillates, but it looks like the amount of CO2 concentration is increasing as time goes on. There's other greenhouse gases such as methane, nitrous oxide, and the CFCs, and this shows the results of studying them since 1978 till about 2010. So we see methane was increasing, but it seems to be leveling off. The CFCs were increasing, but then we stopped manufacturing them, they started to level off. And nitrous oxide is still increasing. The possible effects of global warming will have the climate zone shift poleward by as much as 550 kilometers or 350 miles. This would put heat and moisture stresses and would decrease crop production in certain areas. On the plus side, we would have farms that were productive at higher latitudes. We'd also see rising sea levels. So we know that most things expand when they get warm. So if we heat up the ocean, it's going to expand. Even if it expands just a little bit, there's so much ocean that we'd see an increase in sea level of about 9 to 88 centimeters, or about 4 inches to 35 inches, so that's about 3 feet. So this would be from 1990 to 2100. This would flood any low islands and coastal plains we have. And many of these locations are highly populated. We'd also see a decrease in snow cover and sea ice extent. Both of these things reflect very well. So that energy that's not reflected would be absorbed, and we'd have even more global warming. These graphs show the average annual temperature departures from the long-term average. So we figured out what the average of the Earth should be from all the years we studied, and this shows the departure. Now there's a lot of uncertainty with this hypothesis, and it definitely should continue to be studied. But I don't think anybody will disagree with the fact that if we cut down the amount of air pollution, it has to be a good thing. I mean, for health reasons, for economic reasons. I mean, anything we're dumping out to the atmosphere is waste we're not using, right? So it's definitely a bad thing. So many agree that we should sharply reduce oil and coal consumption, and we should have a greater reliance on non-fossil fuels energy sources, such as windmills and solar panels. And we should make things of a higher efficiency. Therefore, we're not dumping so much pollution out into the atmosphere. So no matter what, if we have a global climate change or not, it can't be a bad thing to decrease the pollution and stop using so much energy. How do we measure the solar radiation? We use something called a pyranometer. This measures the intensity of solar radiation that strikes the surface of the Earth. So here shows the result of one of these readings. This is December 22nd in New York, and we say we reach about a maximum of about 0.6 calorie per centimeter squared per minute. The blue line shows a partly cloudy morning and clear afternoon, and the dark line shows a cloudy day. Okay, so that ends today's lecture on Chapter 3.